So good morning, everybody. Welcome. It's a short course from EUMETSAT, and I have the pleasure to introduce. I'm Federico Fierli, and I have the pleasure to introduce you to Andrea Meraner, my colleague Andrea Meraner, that is a scientist at EUMETSAT, and Sabrina, that is data specialist supporting EUMETSAT that will present today. So just a short introduction from my side. First, okay, what is EUMETSAT? Probably most of you know it, but I mean just a couple of things just to precise who is who. So EUMETSAT is an international organization from '86. Based in Darmstadt, European-wide, and we have the task to monitor weather and climate from space, maintain satellite, but also distribute data, ensure proper uptake of the products, and build know-how. This is one of the actions for building know-how. I can also mention Copernicus. That is one of the programs that we implement. You will see some elements of Copernicus today. And Copernicus is a space environmental monitoring program of the European Union that is based on observation, infrastructure, and services. But I mean, let's go to what we talk today. We talk about wildfire. Probably for large part of you, this is obvious, but just try to put to set the scene. So basically, wildfire is a natural phenomenon that, however, has a strong influence from climate change and the changing condition of the weather, but is crucial for the equilibrium and for the budget of the Earth ecosystem and the Earth system. Just to mention, in Indonesia, basically a fraction that varies from 15 to 40% of the global carbon dioxide emissions was emitted during the fire season in '97. That was exceptional. However, the uncertainty on the emission, as you see, is quite large. So we range between 15 and 40%, and this is the first index of the fact that it is still quite unknown which is the overall impact. I mean, there are strong uncertainty on the overall impact of the wildfire and the changing conditions. Also, there are new paradigms that are emerging. So, for instance, in 2019, we had the first season where the wildfire in Arctic were so intense, with emissions of about 140 megatons of carbon dioxide. And this is an estimate that is coming from cars. Then wildfire, they have a strong role, a key role at the global scale, as we have seen, and this is based on the IPCC 2019. Basically, the climate change is also changing the current and the future fire regime, increasing the wildfire in tropical forests, having prolonged fire seasons. However, what we have observed, and here, I mean, as you see from the top, is the changes in the temperature during the 2019 fire season in Arctic from the C3S service, from the Copernicus Climate Change Service. At the center, you see the smoke plumes that were produced in 2020 in Australia. And here on the extreme right, you see the changes in bird area in Africa. And this is the region where there is the negative trend from the bird area that has decreased in the last 3 decades. However, there is a possible bias in resolution. So the fact that there are changes at a smaller scale that cannot be captured by satellite data that may change the sign or the intensity of this trend. So basically, the point is that it is crucial to monitor, and the satellite is a key instrument for this. Is a key instrument because it really supports the global observation and also to monitor wildfire where there are no ground observations. This is very important for management, for instance. And monitoring from space can be done with different methods, different instruments, different resolution, and different spectral methods. And this is on one previous event. This is wildfire in Greece in 2021, how, for instance, can be observed in terms of fire radiative power, so the intensity in the infrared that is measured is an index of active fires, the redder, the hotter. This is Sentinel-2, and this shows, for instance, at high resolution, the burnt area. This is Sentinel-3 and shows the smoke plumes. And again, here we can see another way to see the smoke plumes in the RGB in false color, coming from EUBEA. And this is aerosol index that is observed in that case in the ultraviolet by Sentinel-5P. I will skip this. I will just mention that satellite detection can be done with the two types of orbits. So the first one is what we have seen just before. So basically it's a polar orbit that is closer to Earth, but has a poorer time resolution. So there is a need for constellation. And for instance, for wildfire monitoring, this is so quite crucial because the observation happens always at the same local time, at the same solar time. And then basically it's difficult to follow the evolution of a phenomenon, for instance, also with the daily cycle and so on. While with the geostationary, we observe the same side of the Earth, but we have continuous observation, as we will see in a few minutes. So basically, satellite, they observe the interaction of radiation with the atmosphere, and basically the presence, in that case, the presence of smoke. So for instance, when we do observe smoke, is seen as an interference on the reflected sunlight. And here is an example on how it can be observed, in that case in RGB. Basically, the parameters you will hear about today are the aerosol optical depth, so the amount of the solar light that is attenuated by aerosol. So then it is directly measured by satellites with the comparison with what should be reflected without presence of aerosol, and is a proxy of the total mass, of the total amount of scatterers. The AI, so the absorbing aerosol index that is observed in the UV, and also you will see a visible imagery component. I will not say much more about that. I will just mention the observation of the total column. So it is possible to observe a total column, the absorption of a total column, and going, for instance, in different wavelengths like UV or infrared, it is possible to estimate the total amount of chemical species. And in that case, this is again at the same season of fires. We can observe, for instance, the nitrogen dioxide, the tropospheric column, the carbon monoxide, that are both produced by wildfire, but also by pollution, as you can see here. This is again Turkey, Greece, Crete, and the Middle East. So you see the pollution here in the Middle East town, but you also see the very strong emissions of NO2, so the large amount of tropospheric column of NO2 that is due to the wildfire. That is backed up by the observation of carbon monoxide that is more persistent, has a longer lifetime, and then you see here that there is a much more concentrated plume of CO. Satellite is very important also to monitor the long-range transport. This is an example of a Canadian wildfire in 2018, and this is the example on how far the plume emitted in Australia traveled up in the stratosphere. Here we observe that the fire were so intense that during the emission they reached the tropopause, and then they were transported in the following months up to 25 kilometer height, so in the mid stratosphere. And here is also the perturbation on the water vapor, and you see it as a sort of tape recorder function of the height and time. And that is from Calliope, from Calypso, that is a LiDAR. You see that this corresponds to a smoke plume that was traveling in the southern hemisphere. So with a potential perturbation in that case to the ozone chemistry and photochemistry. I introduce what we discussed today. So what we discussed today is the recent Canada wildfire event, and we will see it from different point of view. So here is just to show you the visible. This is Sentinel-3 Olchi, that is an instrument that is dedicated to ocean color, but has the possibility to detect smoke, as you see here in brown, and this is the New York area. Here you see Long Island, Manhattan, Bronx, and here is the day where the highest concentration of smoke was recorded in New York, and this is a photo of Reuters. It was early June. And this is how, sorry, this is not moving, or is it moving? I don't know. Yes, it's moving. This is how the plume can be observed in aerosol optical depth. So in this quantity that estimates the amount of extinction from the aerosol. And you see here, this is the AOD that is produced here in the Canada, in the region of Alberta, and then this is transported eastward towards Europe. And we will talk about this story. Aerosol index that I have mentioned before, is measured from GOM2, and again shows the presence of a thick layer of aerosol. Just to tell you, I mean, here you see that we have an AOD that is above 1, is quite exceptional, this level of AOD. So transport from Canada, from US, from North America is not that exceptional, but it's quite exceptional that these values of AOD, and we will see that these will correspond quite well to the burden of emissions. Here you see the aerosol absorbing aerosol index that is very high, is of the order of 3.4 to 3 to 4, and again here is an index of a quite thick, optically thick cloud. This goes together with pollutants because, as we say, the pollutants are also emitted, and this is the carbon monoxide measured from YASI, and this is the plume arrived in Europe. You see it as a strong increase in CO. It is about 5 times the background, and the same here is a formaldehyde. Formaldehyde is also produced by biomass burning activities, and you see this plume of formaldehyde that is much above the background. Just to tell you, okay, how exceptional that was. This is, I mean, a recent communication from CAMS, the Copernicus Atmospheric Monitoring Service, and this shows on the top the evolution for this year of the fire relative power, so the amount of wildfire that were assimilated. That is basically comes from satellite observation and is included in the model, and you see that in different regions, and especially in Saskatchewan, you see a lot of fires starting from the early phase of May, and here you see from 2002, so from when we have the reanalysis, the GFAS reanalysis, the amount of emissions, estimated emissions of carbon, so of carbon monoxide, for instance. And you see that the 2023 is basically exceptional for British Columbia and Saskatchewan. So yes, that was an exceptional year, and in fact, this is quite well backed up, or is quite visible in these anomalous high concentrations. I give the step now to Andrea Meraner, to my colleague Andrea Meraner, that will tell you, okay, this was polar satellites, what we observed from geostationary. And we'll discuss about MTG, the new observation from the flexible combined imager from Meta. So, but before giving you the floor, I just want to mention that we also expect in the next generation the Sentinel-4. Sentinel-4 will be on the sounder, so has to be launched. And this is an example on how we expect, this is simulation, how we expect Sentinel-4 to detect and to observe the wildfire. Here again is in Greece. This is the nitrogen dioxide. So we really expect to have the possibility to have a 1 hour resolution. So a time reconstruction and a near real time following of the, in that case, of the wildfire pollution, columnar pollution. So I stop here. For any question, I think there is a Slido. We will be here to answer, and I give the floor to Andrea, please.
Thank you, Federico. Good morning, everyone. Okay, let me check my screen. Okay. Yeah, so my name is Andrea Meraner. I'm a remote sensing scientist for optical imagery here at EUMETSAT, mostly working on FCI. So I have the pleasure of presenting you the instrument and some first results in terms of wildfire observation. Okay, so I will first give you, let's say, a crash course on FCI Maybe there are some people that are new to the field in the audience, so a brief overview of the instrument, and then we will look at some first examples of observations. Okay, so FCI stands for Flexible Combined Imager, and it's one of the two main payloads on board of the EUMETSAT third generation satellite. The other one is the Lightning Imager. You might have seen the first public release of images a few days ago. It looks impressive as well. So we launched the MTG-I1, so the first satellite of the series of MTG last year in December, carrying the first FCI instrument. And with this instrument, we will go, when we start operations, into full disk scanning service with 10-minute temporary resolution. So this means we will get every 10 minutes a full view of the Earth disk from geostationary position. In a couple of years, then when we will launch the second MTG-I satellite, we will have a second FCI instrument, and with that we will do rapid scanning over Europe. And rapid scanning means every 2.5 minutes. So we will have a view of the upper quarter of the disk every 2.5 minutes. And if we think about the wildfire observation, this is of course very interesting because we can observe the entire fire cycle with very high temporal resolution throughout the fire lifetime. With FCI, we have on a total of 16 channels, so 8 channels in the vis-near domain and 8 channels in the IR domain. The thing with the resolution is a bit complicated, so I tried here to summarize with a table. So we have two modes in the what we call FTHSI mode, the normal mode I will call it. The vis-near channels will come at 1 kilometer resolution, and the IR infrared channels will come at 2 kilometer spatial resolution. But we also have a high spatial resolution mode that we call HRFI, where 4 of these channels will come at a better resolution, namely the 0.6 and the 2.2 at 500 meter resolution, and the 3.8 and 10.5 at 1 kilometer. So again, as you can see on the right side, so we have the IR channels that come at least at 2 kilometer. And here I marked the 3.8 channel and the 10.5 channel, which are typical channels that we use for wildfire observations. So they come at least at 2 kilometer in the normal mode. Then we have the 1 kilometer grid, where we have all the vis-near channels, but also the 3.8 and the 10.5 at higher resolution. So this is very interesting. We will have the main fire channel, 3.8, as we will see shortly, at 1 kilometer resolution, which is quite impressive, and we can this opens new doors for wildfire observations. But we, as mentioned, we go one step further. We have 2 channels at 500 meters. In particular the 2.2, which is also sensible to fires, in particular the hotter fires. So we will have the possibility of observing some fires at 500 meter resolution. Of course, when we talk about geostationary satellite in particular, the resolution is always at nadir, so at the sub-satellite point in the center of the image. The resolution gets worse, or the pixels get bigger the farther away you go from the center of the image. But still, it is still quite powerful, even at, let's say, European latitudes, for example. Okay, so a few more details on the 3.8 micron channel on FCI, because this is the main channel that we use to observe fires, since it's the most sensitive, in particular to subpixel wildfires. And during the instrument design, the particular efforts were made to increase the performance in terms of fire detection. So, as said, compared to Severi, which is the predecessor of FCI on board of the second generation of EUMETSAT, we go from 3 kilometer to 1 kilometer resolution, which means we have 9 times more pixels. Also, the saturation temperature, which is interesting when we look at hot fires, will increase from 335 Kelvin to around 490 Kelvin. The channel is also a bit more far away from the CO2 absorption band, so we will have less problems with cooling and limb cooling. We have a better radiometric resolution. So for this specific channel, we have 13 bits per pixel instead of 10. And also, since MTG is 3-axis stabilized and not spinning like MSG, we will have less blinding effect, which was problematic with Severi. Okay. And here, just to mention, of course, we will produce the level 1 images, which are the, let's say, the plain channel observations in terms of reflectances, brightness, temperatures. But we also produce some level 2 products in-house, so some extraction of geophysical parameters. In particular, as we had on Severi, we will have also for FCI an active fire monitoring product coming every 10 minutes with a resolution of 2 kilometers. And the moment we will go into operations, we will have the chance, we will try to develop and further improve this kind of products. And particularly here, thinking of the resolution, we will try to get more out of the instrument. But of course, in the SAF network, we also have the LandSAF, LSA SAF, that produces a suite of products from MTG FCI related to wildfire observations. So I invite you also to check out the products by the LSA SAF list. Okay, so this was the introduction. I would like now to show you some first FCI imagery. Let me remind you, this is imagery from the early commissioning phase. We are still working and tuning the instrument. So the geometric and radiometric quality is still preliminary, and we are still working on it. And the images you will see were all produced using the Pytrol framework. It's a suite of open source Python packages useful for any type of meteorological satellite Earth observation data processing. And also I used the open source visualization software SIFT to produce some of the images that you will see. And actually, around a month ago, we gave a short course on this SIFT tool. So if you're curious and want to reproduce some of these images, check out the training course. There is the recording and all the informations are online. Okay, so let's start with the images. I suppose most of you have seen this image. It's the first acquisition, the first image that we have released. And we're now gonna zoom in into this area in the Sahel region. And because there were quite some fires going on during that day of the first image. And this is a video. Let's see if it starts. Yeah. Okay, so what you're seeing here is the true color in the background. So the visible channels combine to create this realistic viewing image. And on top, I have put a layer showing the fire temperature using the 3.8 and the 2.2 micron channel. So we can clearly see starting from lunchtime until the evening how a lot of wildfires develop and spread over this region. And particularly, I might point you to this big one up there. And here we see how fire starts and develops, starts producing a lot of smoke, leaves a burn scar behind him, and then towards the evening slowly comes to an end. And here, again, coming back to the temporary resolution, we have one frame here every 10 minutes, so we can really observe how the fire starts and spreads in which direction. And this is one of the big advantages of geostationary satellites. So let's look a little bit closer to that big fire. Oops. Okay, there you go. My slide was stuck. So I took for the same period the Severi data, and I plotted it the very same way with the natural color in the background and the fire temperature, of course, only with the 3.8 channel because the 2.2 channel is new on FCI. So this is what Severi sees for that fire. And of course, it detects the fire since it's a very big one, but the resolution is very coarse. And now I will switch to what FCI sees. And I think the jump is extremely impressive. Let me go back again to Severi and again FCI. Here we see the resolution jump as first. Of course, we go from 3 kilometers to 500 meters since I'm using the new 2.2 channel. And yeah, the amount of detail that we can recognize from the fire is astonishing. At the top, we can also recognize the burn scar behind the fire and the fire core, so we can actually see where the fire is still at the hottest. And we can detect some smoke due to the shortwave channels in the true color of FCI. We will look at it a bit later. Okay, this image is from a more recent date, around 10 days ago. It's from 1st of July, 13 UTC. And what you're seeing here is the so-called fire temperature RGB. So it's a combination of the 3.8, 2.2, and 1.6 micron channel to give a colorized impression of the fire temperature. And well, you can clearly see in the entire Central South African region a lot of fires. And if I zoom in, we can also recognize the core of the fires and the higher temperatures going from red to yellow and whitish colors. And of course, this is an RGB, so it still needs some tuning. We are looking into it. So basically to adapt the representation to the specific FCI channels. So this is still very preliminary, but it's an interesting visualization technique. Okay, now onto the other aspects of wildfires, so the smoke, as Federico introduced. We have been looking at this smoke transport from the Canadian wildfires using FCI. And two of the new channels that we have on FCI, so the 0.4 and 0.5 micron, they are useful to make pretty imagery. So the true color with some nice realistic looking colors. But they're also very useful to detect smoke since the scattering is stronger at this wavelength with the smoke. And we can clearly see in this animation how after 27th of June, how the smoke is being transported from Canada and is slowly reaching France and Spain. And we can recognize it in some gray looking colors. As a comparison, this is a natural color RGB. So this is the RGB that we will have used with Severi using the channels available on Severi. We can still see the smoke actually, which is also an indication of how thick it was, as Federico was mentioning, since usually with Severi, it's harder to see this kind of smoke due to the absence of the 0.4 and 0.5 channels that are more sensitive to it. And yeah, in this representation, we can recognize it in bluish, semi-transparent colors. And to further look into this difference in the channels, I have taken the single channels from one of the frames of these animations. And I'm starting here from the 2.2 channels in the near infrared, and I will go to shorter wavelengths towards the visible. So we can already spot the smoke plume around this area, even in the 2.2 channels. But if I go towards the 1.6, we can clearly see how the smoke plume becomes more evident. Here I'm at the 0.9 channel, even shorter 0.8, 0.6. Here it's very clear. And on the new channels for FCI, this is the 0.5 channel and the 0.4 channel. Of course, we see the effect of the Rayleigh scattering appearing, but also the smoke plume becomes more and more evident. Okay, that was it from my side. And yeah, I thank you. I leave you with this video of the day after. So this is the 28th, I believe, where the smoke plume already passed Spain and was reaching Italy. Thank you very much. I think I leave the floor now to Sabrina.
Thank you, Andrea. Hello, everyone. Thanks again for joining us. So I'm going to share my screen now.
You can grab it.
Yep. So we're now coming to the third part of the wildfire short course, and we'll be looking at some resources we have for you, as well as some data visualizations from fire case studies. So I'd first like to introduce you to two sets of resources we have online. The first one is a Jupyter book focusing on the next generation satellites that both Andrea and Federico mentioned, both MTG as well as EPSSG. And then we also have a fire case study from last summer, in Gironde, France. And then I'll show you some data visualizations similar to the images you've already seen today in a short demonstration. So first, a little bit about the Jupyter book. So we've prepared this online set of case studies for you that cover different parts of the fire life cycle, everything from pre-fire risk to active burning, smoke transport, as well as monitoring burned areas after a fire. And this is available online at fires.trainhub.eumetsat.int.
Sabrina,
don't worry. Yep.
Apologies, we can't see your slides.
Oh, okay.
Yeah, I was going to say the same. Thanks,
That's
Julia.
strange. Okay, let me try that again. Okay, do you all see my slides now?
And not on slide mode yet, but
yeah, but you see the screen, right?
Yes, exactly. Yes,
okay, excellent.
Thank you.
Okay, sorry, that didn't work before. Okay, so like I mentioned, we have three parts, and then now I'm going to the first part, which is the Thanks Jupyter book. So this is a screenshot of the Jupyter book, and you can see the link here. I will be, Rosa will be pasting these links at the end, so don't worry about getting any of these links. You will have them in the chat and probably in an email afterwards as well. So like I mentioned, they cover different parts of the fire life cycle. And there are two case studies here on this Jupyter book. The first one is the California fires in 2020, the major fires, the August complex caused by lightning, and then the Mediterranean fires in 2021, where both Greece and Italy were heavily impacted. Oops, sorry about that. So each case study also introduces the upcoming instruments that both Andrea and Federico shared about, but we are using proxy data sets because at that time we don't have any data from the actual instruments available. So for example, here for this case study in California, instead of MTG FCI, we use the GO17 AVI instrument as a proxy. And in addition, you can actually see how each of these figures were made. So here we also included some complementary data sets like Sentinel-2 to look at burn severity. And at the end of each image in the caption, there's a link. And if you click on this link, it will take you to a Jupyter book, Jupyter notebook that shows you step by step how we created this image or this plot. And you are also able to execute these workflows by clicking on the link here in the hint box, which will take you onto a separate Jupyter Hub-based platform, which has the data already loaded on it. So you can actually run through the notebook yourself and see how these images were created. We'll be using a very similar platform today, later when we look at the Canadian fire plots. So In addition to those two case studies that I mentioned already, we also have a case study devoted to the fires in Giron last year. And I welcome you as well to click on this link later on when you get the PowerPoint to explore this case study to also see how the fires can be visualized using different products as proxy data for MTG and EPSSG. Okay, so without further ado, I know a lot of you might be here also to take a look at the data visualizations. I'm going to go through the 5 that we have prepared, and afterwards you can then answer a poll. Because we won't have time to go through all of them, we'll pick maybe the top 1 or 2 to see which ones you should go through. So the first visualization is the Sentinel-3 Olchi True Color composite that Federico already shared. So this one is taken on the 7th of June, and you can see the smoke coming down to New York, causing those orange skies. So this is the first image. The next product, Federico also shared as an animation, but here we have a still plot coming from the Sentinel-3 SLSTR aerosol product. So you can see here aerosol optical thickness, or AOD as well, aerosol optical depth at 550 nanometers. And again, this is more of a zoomed out image. You can see that the smoke here is also coming downwards, southwards towards Long Island. And there's a lot of smoke over the same area taken from the same day. The third image that we can explore is the Sentinel-5P Tropomi Ultraviolet Aerosol Index. So once again here, this is all taken from the 7th of June. And you see the smoke plume again coming over the same part of the northeastern US. Okay, the fourth plot is an animation. And this is taken from the CAMS Global Forecast. So we have organic matter, aerosol optical depth, and you can see the long-range smoke transport with the smoke traveling from Canada and northeastern US towards Europe. And this is again on the 27th of June towards the 28th of June, following the forecast. And this forecast goes for up until the 29th of June, so you can see how it was forecasted to develop over time. Okay. And finally, we also have the MSG Saveri True Color RGB image as an animation. Here, showing you how the smoke plume was also transported towards Europe. So you will also be able to create animations like this, following the workflows that we have prepared for you. Okay, so I've gone very quickly and shown you the 5 different data visualizations. And now I'd like to invite Rosa to take the screen and put up a poll to show us these options, and you can all vote on the data sets or the data products you would like to learn about. So I'm going to give everybody a couple of minutes just to get here. You can go to this poll by going to slido.com and typing in hashtag EUMSC41, or on your phone, if you have a QR code reader, you can scan the QR code and it'll also take you right to this page. So I'll give people 1 minute to respond. So far we have 9 responses. I know there are a lot of people here, so I'll give you all a chance to also get in your responses. Okay, it looks like so far the top data product that most people are interested in, the CAMS animation showing the organic matter AOD from the forecast dataset, followed by the tropomi aerosol index from Sentinel-5P, and then the Sentinel-3 AOD dataset. Okay, last chance. Anybody want to get your votes in? If not, I will start off with this animation from CAMS. Okay, so let me go back to sharing my screen again. Okay, so once again, here are the links. And now I'm going to ask Rosa to paste in the chat some of these links. And I invite all of you to go to this link over here, login.ltpy.adamplatform.eu, because we'll be looking at preloaded Jupyter notebooks that are already on our training platform. So if you can please go there and log in if you have an account, or make an account if you don't. I will now also share a different screen to show you what that looks like. Okay, so you will end up here on this particular screen, this landing page. And if you don't have an account, you can sign up for a new account by clicking on this link. However, I already have an account, so I'm just going to go ahead and log in. And there are 3 pictures you will see, 1, 2, and 3. We're going to click on the middle one that says training.ltpy.adamplatform.eu. So this is the training platform that we will use. So click on this middle link, and it'll take you to a Jupyter lab. So I'm going to go through the CAMS Global Forecast animation. And all of these notebooks are available in this folder. So when you first log into the platform, you'll see in your workspace here several folders. So today we're working in the Wildfire short course folder. So if you double click on this Wildfire short course folder, you will see all the notebooks that we have for you here. And the CAMS Global Forecast notebook is number 4. So double click on 04, and it will open up this notebook over here. So each of these notebooks gives you some information about the data set, as well as the case event, in which case this is the Canadian fires. And it also tells you some basic facts, such as the spatial resolution, the coverage, the data format that you will be able to download this data in. And we also give you some information about how to access the account. So in this case, the CAMS data is available via the Atmosphere Data Store, or the ADS. And you first need to create an account before you can access the data, either manually by downloading it from the web interface, or using the package CDS API to programmatically download this data. So in this workflow, we'll show you how to download the data programmatically. And then we will visualize it afterwards. So here we have the set of libraries that we require. And we'll be using Xarray to open the data, as well as Matplotlib and Cartopy to visualize this data. In addition, we have a set of functions that we have prepared for you. So if you double click on this functions notebook on the left here, you can see these functions, and they are basically convenient functions that help you either open data or visualize data and create a subset, for example, over your area of interest. This one is something we will actually be using later on in some of these notebooks. So feel free to explore the functions notebook. You can reuse these and modify them to your needs. So the first step to download the data is to log into your account after registering. And then you can copy your user ID and key, which is available on this page here, this API how-to page. Then you paste in this unique key that is your personal key. and you can start to download the data. So I will not run these because we have already pre-downloaded the data. This API request you can actually obtain via the web interface. So if you click on this link, it takes you to the web interface. And if you go to download data, this set of boxes will appear. And you can then specify, for example, what are the different variables that you want. In this case, it's the organic matter, aerosol optical depth, and the dates that you're interested in, the time selection for the model run you want, and the lead time hour. So in our case here, we have basically picked every 3 hours, and we are downloading this data as a zip file, a zip-to-net CDF. So after you have selected all the boxes that you want, you can click on Show API Request, and an API request will appear over here. So you can actually copy this lower part here and paste it into your Jupyter notebook. One important thing to note is that you need to always include this URL here and the key so that you can access these credentials to do the download. And then you can also change the bottom part here to specify where you want to save this zip file. So after you have downloaded the data, you can use this set of code here to actually unzip it. Again, we have commented this out because it has been already unzipped for you. And then once you have done that, you can begin to visualize the data. So I'm going to start from the top here again to run these 2 cells. So you can run a cell by either clicking on this arrow button or Shift Enter on your keyboard. So the first step we do is that we are going to open this file using Xarray, and we passed in the path of where this file is kept. So now you can take a look and see inside what are the coordinates, the dimensions, and the variables that are available. So in this case, we know we've downloaded the correct one. It's OMAOD 550. And there are a total of 41 time steps. So you can see these are the 41 time steps in the data. You can also take a look at other attributes like the latitude and the longitude. So you can see that this matches what we have seen before with the 0.4 degree resolution. And the longitudes are disseminated in a 0 to 360 degree grid. However, if we want to plot it, we need to first bring it into a minus 180 to 180 degree grid. So you can use this following code cell here to actually assign the coordinates to have new values. And now you can see that the longitude starts from minus 180 to almost 180. And this is different from where it was before, where it started at 0. So next, we need to retrieve the data variable that we're interested in. And we can do so using these square brackets over here. And when we run this particular code cell, you can see that we have now retrieved the data variable OMAOD 550, and it has some attributes. It has units, which are just as tilde, so it's unitless. And the log name is also available here. We can actually save these attributes to use in the plot later. So let's do so. So here we save the OMAOD.longname, this long name inside this variable here called longname. And we also save the units. And then we can do the same for the latitude and longitude. Okay, so now we can visualize this. And we are going to use one of the functions that we used before, the visualize p-color mesh function that we have saved here in the functions library. So it's available here. And if you want to take a look and see what are the arguments you need to use, you can always just use a question mark with the name of the function, and it tells you exactly what the arguments are and what it does. So remember, we have 41 time steps in this data set here. So we can actually set the time index to a different number, and it will show us a different slice in time of this data. And we can use the function visualize p-color mesh again and specify a few arguments to be put in. So earlier on, we saved our longitude and latitude, and so we can pass them back in here. We also saved the units, and then we saved the long name. So these are things we've saved before. And we're going to add a space here, plus some information from the time index. So we clipped the time index to only show this part here. So we have the date as well as the time by specifying to what position in the string we should stop. We also set the projection, which is CCR as plate carré, and the color scale. So you can again modify these things to show your data in a different way. Of course, like I mentioned before, we're using the OMAOD data with a time index of 10. So in this case, this is the 26th of June at 6 o'clock in the morning. You can also set the minimum and maximum values of this color bar at the bottom. So here we've set it to a minimum of 0 and a maximum of 2. And here is the result when you run this cell. So you can see already that the smoke from Canada is midway in the Atlantic Ocean and is being transported towards Europe. Okay, so that was the global image, but what if we want to zoom in to just this area in the Northern Hemisphere to just look at the smoke plume? So again, we'll use a function that we have in the functions library, the generate geographical subset, and it needs the data set you're working with, the minimum and maximum latitude and longitude for this bounding box for where you want to, in a way, zoom into or clip to. And in this case, we have selected these values here to give us a bounding box across the Atlantic Ocean. So we can run these two code cells. And if you take a look at the data array again, you see that there are now fewer values. So it starts for the latitude at 80, and the longitude as well starts at 119, negative 119 to 30. So now let's do the same. Let's visualize it and see what it looks like. So here's now the subsetted data. And at a different time step where you can again see this smoke transport. So now that we have created the data set, we can animate it. So our 41 time steps will now become an animation. And we can then use these steps here from this animation function. So you can set an initial state, which is the first plot, and then animate over the entire data set. And then finally, it will be saved as an animate.func animation object, and you can save this as a video later on. So this takes quite a while, but then once it is done, you can play the video as a HTML. I've already exported it, so I'm just going to play it here. And this is the same that you will see in the PowerPoint. So that was an extremely quick flyover of the workflow for creating this animation. And all these links will also be available to you at the end of the course. I'd like to now turn the floor back to Rosa so that we can have just a few minutes for questions. So thank you all for your attention. Okay, so we have a couple of questions here, and the first one is for Andrea. Andrea, when do you think the new active fire products will be available? It's a question from Max.
Hi, Max. Yeah, good question. So as I mentioned before, we are still in a commissioning phase for FCI, and we will be until end of the year. That's the current plan. There is actually a website now on the EUMETSAT page giving you an updated timetable for the release of both the level 1 and the level 2 products. I believe if you Google MTG data, EUMETSAT, you will find it. I think the current plan is to have the first level 2 releases towards November. So late autumn timeframe.
Okay, thank you, Andrea. And the next one is also for you, and the next two actually. So from Amir, how long does it take from receiving the image to the detection of fire in terms of processing? And the second one is there a way to access the results, or is there an alarm system for responders working with the fires?
Okay, so regarding regarding the first question, so for the level 2 production, we have, of course, timeliness requirements, and I believe it is 20 minutes after end of the acquisition at most. So worst case, there will be 20 minutes delay until the products are disseminated since the end of the image acquisition. But of course, we will have to test this now also during commissioning, and I believe we will probably have better performance, but yeah, we have to see. And for the next question, if there is a way to access the results or any alarming system. So the data is disseminated via EUMETCAST. In principle, anyone can set up his own reception station and get the products and read them, and then integrate them into a national warning system, etc. So I think this is something that each let's say each wildfire monitoring service needs to implement themselves. I believe there is also a centralized page where all these detections are collected from different satellites, but I'm not sure about the timeliness of it. Maybe Federico or the other panelists know more about this. Okay, since not.
Yes. No, basically one of the things. I mean, you are made probably aware of the EFIS system. I mean, it was not presented here. EFIS is the service from the European Commission that is implemented by the GRC and has early warning, and you can also, for instance, see the fire distribution in that case from MODIS. Similar services provided by the NASA, but again for the fire points are again MODIS, so is one per year. So these systems are there, are not, to my opinion, are not complete. And one of the things is really, I mean, we need a better integration of the satellite data. I mean, you have seen from Andrea. Okay, it is smoke, but there are also the fire pixel, and I think a better integration with the geostationary data sets that have, I mean, a latency that is relatively short, so can be used for the alarming system where especially you don't have a ground-based network. It should be absolutely important. I mean, for you, I also have to say that, I mean, most of the alarm system is based on the ground-based observations. So it's so on the network of visual observation of fires. But I mean, for sure, satellite is crucial in regions where you don't have this. So especially in the northern region, in the Arctic area, where I mean, basically are inhabited, but there is still a strong impact. That's it. There is another question for you, Andrea.
Will there be level 2 FCI fire products at this resolution? I see in the docs there will be a 2 kilometer product, I guess, for the IR radiative power, but 0.5 or 1 kilometer detection would be good. Hi, Simon. I totally agree. So I can speak for, let's say, the EUMETSAT's active fire monitoring product. I believe there is no clear timetable on when and how to improve the product yet. We will start with these activities after the end of the commissioning. I'm not sure on the Landsat side what they are planning to do there. I invite you to contact them directly for this question. But I totally agree. It would be good to integrate the high resolution and have a high resolution product. And I think this will be one of the first things we will tackle.
Thank you, Andrea. So we have a few questions regarding the training files. So, and the workflow. So for the plume globe visualization, I believe Andrea and myself, we use the same libraries to make it. So he mentioned the PyTrol libraries, and in particular SatPy. You can also then take a look at the workflow that's on the training platform to see exactly how we open the data and turn it into an animation. We also have these workflows available online at the EUMETSAT GitLab. So you'll all get a link to this after the course, where the notebooks will be permanently located, and you can download the notebooks or clone the repository to your own laptop or machine for future use. So the training platform that I shared with you, it will not be always there because we reuse this platform for other trainings. So you can try it out now. It'll be there for a couple of weeks. But if you want a long-term copy, please download and save it onto your own laptop. And someone mentioned that it's not working. I think there's a problem in the link you shared. I think you have a typo in there. So instead of platform, you have platform. So this might be why it's not working. But if you have any issues, feel free to, again, contact us after the course and we can see what's going on. It might be you need to first make an account and log in. So that might be another issue. And lastly, there's a question from Monica to Andrea. Is this about the data? Will it be open access?
Federico, correct me if I'm wrong. So in principle, yes, anyone can create an account and download the data from the data services and the archive. I think for the near real-time reception on EUMETCAST, there are some license rules. Federico, maybe you can fill in on that.
Yes, through the data store, the dataset will be distributed in different ways. Through the data store, you can make your own account. Datasets will be in a CDF, and then you can download them from, using API or, just browsing. They will be visible from EUMETView. I think there will be a latency, so not a latency. There will be a storage, I think, of a couple of months on the EUMETView. I don't remember precisely. And then you have the EUMETCAST that is for let's say professionals, or but this is let's say the other official channel that is but more for the services, and will also be made accessible through the weather services of the different countries. But yes, the answer is yes. Data are principle of access.
Okay, are there any last questions? Looks like we have answered all your questions. So I'd like to thank again everyone for your attention, and I turn the floor back to Federico to close this short course.
It's really not official. Thank you very much. Thanks, Sabrina. Thanks, Rosa, for supporting. Thanks, Andrea. And yes, it was a pleasure. I don't know if there are additional short courses that will be held before the summer break. I don't know, Rosa, if you can just notify or tell us if there is another one, so we can announce it. If not,
yes, there is one on
there is one.
Yeah,
okay.
On 19th of July on warming oceans. So at 11 UTC. So okay, the last short course then, for the summer.
Yeah, and then after the warming ocean, we can go to we can probably all go to vacation, taking care of the heat waves and it's a bit tough in this period. Okay, have a good day, have a good lunchtime. Thanks again. All the material will be available on the training, so the presentation and the recording will be there. And also all the notebook, all the material is also available. The Jupyter Lab, as Sabrina said, is available only for a limited amount of time, but I mean the space can be replicated on your own place. Just one last point before going, just take 1 minute to fill the evaluation poll that is important to us to try to improve on what we do. Okay. Thank you very much. Have a good rest of the day. Have a good end of the morning. And thanks again, Sabrina, Andrea, Rosa, and Julie as well, and everyone who has followed the session today. Bye.